Alright, today we're going to have a look at simple harmonic motion. Now, simple harmonic motion describes particles that are oscillating in one dimension, usually vertically or horizontally. Now, there are really obvious examples of simple harmonic motion like tides rising and falling, and less obvious examples like vibrations in a string. So simple harmonic motion, you imagine you've got some object moving between two fixed points and it's moving back and forth and back and forth and back and forth and back and forth like that. So if you were to graph simple harmonic motion, more generally it would look like this. So simple harmonic motion, we can see we've got an object. Now it doesn't mean it's literally following this path. It means that this is x along here, and this is the center of movement, and it's moving up and down and up and down. So if we were to have a look at its motion, it would look like this, moving back and forth and back and forth. Most obvious example is tides. And also you've got other things like AC current, which moves up and down with electrons in a current. Now you might wonder, okay, well, what type of equation can describe something like this? Well, what does that look like? It looks like a sine curve. And that's exactly the type of equation we use to model simple harmonic motion. So it's clear from those above examples that this can be modeled with sine and cosine curves. Now, simple harmonic motion can be modeled with the following equations. Number one, we've got x is equal to a sine of nt plus alpha plus c, or x is a cos nt plus alpha plus c. Now, a few different things. We've got x is the displacement from the fixed point, which we call the origin. The period, obviously, is going to be 2 pi on n. Alpha on n is something we call the phase shift, and c is the center of motion. This phase shift is something that a lot of time we don't really care about. Usually we set the phase shift to be 0. Generally, the phase shift is used when we want to compare two equations of motion and show that they're the same graph. It's just been shifted one way or the other. And in fact, the difference between this equation and that equation is that one of them's just been phase shifted by pi on 2. And c is the center of motion. Now, you might wonder, why is the phase shift alpha on n and not just alpha? Well, the way we solve equations, if we wanted to know the phase shift, well, the phase shift is another way of saying how far has my graph been shifted. And another way of asking yourself how far has the graph been shifted is asking yourself how far have the roots or the solutions, the x-intercepts, been moved. And if we wanted to find the x-intercepts, we would do something like this. But in a similar way, if we had a look at a graph that had been phase shifted, we would solve this equation, and that gets us a on n. So that n is being divided by the alpha, which is why it's alpha on n and not just alpha. Okay. Now, we've got an equation of motion that we've decided describes simple harmonic motion, and let's say we wanted to know the acceleration, and the formula we're about to derive is very important, and it's on the reference sheet. So x is equal to, we've said our definition of simple harmonic motion is a sine nt plus alpha plus c. Now, an important note that a lot of students get confused with is this a is not the same. That's an alpha, that's an a. Don't get confused between your amplitude, which is how far up your graph is going or how far away from the center of motion you're going, and this is alpha, which is your phase shift. And we want to know acceleration, which is the second derivative. The first derivative is going to be a n cos nt plus alpha, and the c goes away. And x double dot is going to be equal to minus a n squared sine nt plus alpha. Now this part here almost looks the same as this. And it almost is. So what if we said, okay, this was minus n squared, and we've got a sine nt plus alpha, and to make it the same, we would need a plus c. Now this is the same, but we can't just randomly add a c, so let's minus the c. Now this here is what we originally started with. So here we've got minus n squared x minus c. And this is very, very important. This is on the reference sheet. This is the formula for acceleration in simple harmonic motion. Okay. So as I've just said, this yields a very important definition for simple harmonic motion. Now we're going to start by assuming that the simple harmonic motion is horizontal along a number line with the positive direction to the right. Now we can easily adapt that, obviously, to vertical motion. Now a few definitions. We've got the distance from the centre of motion c to either end is called the amplitude, and the centre of motion is also known as the equilibrium position, or the position of equilibrium. Okay, we've just stated that the acceleration of a particle in simple harmonic motion is directly proportional to the distance from the centre of motion and directed towards the centre. You might think, directed towards the centre, how's that? Well, if we define its motion as positive, well, towards the centre is going to be negative, which is where that minus comes from. Okay. Speed, the important definition about speed in simple harmonic motion. The speed of the particle is 0 at the end of motion and reaches the maximum speed at the centre. This makes sense as the stationary points are at the end of the equation of motion where dx to t is 0. Okay. The second example today, we need to prove that this particular particle is in simple harmonic motion. And to prove that something's in simple harmonic motion, number one, we can prove that its displacement equation satisfies our general definition, or more commonly, we're going to prove that it satisfies our acceleration equation. So we've got x double dot is equal to minus 16x minus 4. Let's pull out a factor of minus 4. Minus 4. X. Actually, we want to. So if we have a look at our definition for simple harmonic motion, we've got x double dot is minus n squared x minus c. Now notice that the coefficient is 1. So we're going to have to pull out a factor of minus 16. So that's going to be x plus, if we pull out 16 from 4, we're going to get 1 on 4 there. Now we're going to say this is now simple harmonic motion as it's minus 4 squared x plus 1 on 4. So this describes simple harmonic motion with n being 4 and the centre of motion being a quarter. Okay, an important note about our acceleration. Many questions do not need a value for alpha. Alpha is generally used when comparing two curves and how they could be the same curve but shifted along the axis. In most cases, we're going to let alpha to be 0. Now, in a lot of cases, the centre of motion is 0. It's literally the origin. So we're going to, a lot of the time, see x double dot is minus n squared x minus 0 because the c is 0. All right, our third example is we've got a particle moves in simple harmonic motion with centre motion 2, amplitude 3, and period pi on 2. Find an equation of motion. Okay. Equation of motion means our x is equal to a sine nt plus alpha plus c. Now again, it doesn't say phase shift anywhere, and we don't really care about phase shift that often. So this is going to be 0. Don't really care about that. But let's have a look. We've got the centre of motion is 2, so we already know that the centre of motion, that c is 2. And the amplitude is 3, so a is 3. And we just need to know the value of n. Now the period formula, we've seen this in year 11 advanced, is 2 pi on n. So 2 pi over, well, we know the period, is equal to pi on 2. So pi on 2 equals 2 pi on n. So that makes n equal to 4. Is it? No. Is that right? The pi's cancel. Yeah, n is 4. So therefore, my equation is x is equal to, the amplitude is 3 sine. The n we've said was 4 t, alpha was 0, plus the centre of motion is 2. Okay. Now, technically, you could have any value of alpha here and it would still be the same equation, but we can't be bothered with that. It's easier just to make it 0. All right. The next example, what have we got? We've got a particle moves in simple harmonic motion about the origin with a period of pi seconds and an amplitude of 5 meters. Find the maximum displacement, velocity, and acceleration. The best thing we need to do here is form an equation of motion. So we know simple harmonic motion exists most generally in the form A sine nt plus alpha plus c. Now our alpha don't care about phase shift really, so that's going to be 0. What do we know? We know its period is pi, amplitude is 5, and its simple harmonic motion is about the origin, so that means our c is 0. We just need to realize that the period is pi, so pi is 2 pi on n, which means n is 2. So my equation is x is equal to 5 sine 2t plus 0. Okay, now we can start the question. Let's find my maximum displacement. Okay, now the maximum that a sine curve can be is 1 and minus 1. And if the amplitude has become 5 and it's about the origin, then our maximum and minimum is going to be 5 and minus 5. So x is going to be between minus 5 and 5. So that's our minimum. Oh, what's going on there? Minimum and maximum. Now, obviously, a different center of motion is going to affect this. If it's plus 1, if there's a plus 1 here, well then it's going to be between minus 4 and 6. If you're stuck with that, you can just differentiate it and make it equal to 0 and you'll get the answer. But really, the maximum is just the center of motion plus the amplitude. The minimum is the center of motion minus the amplitude. Maximum and minimum velocity, we're going to have to differentiate my equation, so that's going to get x dot is equal to 2 times 5, which is 10 cos 2t. And we want to know the maximum minimum velocity. Now, I guess you could differentiate that a second time and then a third time to find the maximum minimum acceleration, but let's just think about this logically. This is my equation for velocity, and the maximum that my velocity, that cos can be, is minus 1 and 1. That's the range, minus 1 and 1. So in this instance, it's going to be minus 10 and 10. So the maximum is going to be 10, and the minimum velocity is minus 10. Oh, that's the wrong way around. Maximum 10, minimum minus 10. Yes, you could differentiate, make it equal to 0, you'll get 10 and minus 10, but this is just saving you time. Okay, part 3. We want the maximum acceleration, so let's differentiate again. We're going to get minus 20 sine 2t. Look, again, this is just a sine curve. The maximum is 1, the minimum is minus 1. The fact that it's minus sign doesn't change that at all. You're just going to flip it upside down, but the maximum is still 1 and the minimum is minus 1. So my acceleration is going to range between minus 20 and 20, which makes my maximum acceleration 20 and my minimum acceleration minus 20. Okay. Yes, you could find the third derivative, set it equal to 0, and you'll get those answers. Okay. Next example, we've got a particle is moving in simple harmonic motion about the origin with displacement given by that. What is its initial displacement? Well, don't be fooled. Initial displacement does not mean the origin. It doesn't always start at the origin. It might start at the origin sometimes, but not all the time. Initial just means when t is 0. So we're going to set t to be 0. So 3 sine of pi on, or 0 plus pi on 4, which is going to be what? 3 root 2 on 2. So that's my initial displacement there to x0. Initial velocity, we need to differentiate to find my velocity equation. Remember, velocity is the differentiation of displacement, so it's going to be 3 cos t plus pi on 4. That pi on 4, which is a phase shift, doesn't affect my differentiation at all. And what do we want to know? We're going to set, we want to know the initial velocity, so x dot 0. We're setting t to be 0, so 3 cos of pi on 4, which again is, well, cos of pi on 4 is 1 on root 2, so this is going to be 3 root 2 on 2. That was nice and obvious. What have we got? Once its velocity is 0, how long does it take to reach the origin? Okay. All right, so let's have a think about this question. So once its velocity is 0, couple ways of doing this question. You could set the velocity equation to be 0, find the time, and then find the time it takes to get back to the origin if you knew when it gets to the origin. You probably could get the answer that way, but it's going to be really, really tricky. Think about, though, what happens in simple harmonic motion. We've said at the either endpoints of your simple harmonic motion is when your velocity is 0. So your velocity is equal to 0 at the endpoints of the motion. So your velocity is 0 here and here. And the center is here. That's my center point. Now the definition of a period is how long it takes to go from here to here and back to there. So if I want to know the point to go to the origin from a velocity is 0, in other words, it's asking how long does it take to get from one endpoint to the origin. Now, if the period is all the way here and all the way back, only to the origin once is going to be a quarter of your period, so period on 4. So we need to know the period of motion in this instance, and the period is 2 pi on n. And n in this instance is 1 because there's no... Oh, God. Sorry, I don't know what happened there. Where are we? Here. N in this instance is 1 because there's no coefficient of t. So we've got 2 pi, and the time is just going to be 2 pi on 4, a quarter of a period, which is pi on 4, well, pi on 2 seconds. That one required some abstract thinking. They're really showing that you understand the concepts. You probably could have got it another way, but that's going to be the quickest way. And really what's going to set you apart in an exam to do questions fast. Okay, example 6 today. We're going to have a look at a particle moving in simple harmonic motion centered about the origin. Now, when x is 4, the particle is at rest. When x is 2, the velocity of the particle is 4. And we want to know, really, the equation of motion. Okay, all equations of motion, we're told in this instance, exist in the form a sine nt. That tells us that, first of all, the center of motion is 0. The question does tell us that, though, centered at the origin. It also tells us there's no phase shift. We might read, the question tells us that when x is 4, the particle is at rest. Again, we're thinking, okay, what does it mean for a particle in simple harmonic motion to be at rest? A particle in simple harmonic motion is only at rest twice in its motion at either endpoints. So if x is 4 when it's at rest, that is telling me the amplitude is 4. So my equation so far is 4 sine nt. Now we know that when x is 2, the velocity of the particle is 4. Let's highlight that. When x is 2, the velocity is 4. We can't really use that at the moment because we don't have a velocity equation. So we do need to find that x dot is going to equal 4n cos nt. Don't forget about that n there. We don't know what it is, but when we differentiate it, we do have to bring it out the front because the differentiation of nt is n. Okay. Right. So we do know that the velocity is 4 when x is 2. So the velocity is, 4 when x is 2. So we've got x is equal to 2. X dot is equal to 4. So I guess we can form two equations here. Up here, we can't really solve either of these because we don't have enough variables, I guess, to solve them. So we're going to have to form two equations. if we have a look here, we know that x is 2, so we're going to have 2 equals 4 sine nt. That's using our x coordinate. The reason we can't just substitute both of these into here is because this is velocity and that's n. We can't use this x. We can only use the x up here. And then over here, we've got velocities 4 is equal to 4n cos nt. Okay, so that's going to give us two equations. This first one, I'm going to highlight that in yellow. If we simplify that, we're going to get, sine nt is equal to 1 over 4. And if we simplify the other one, we're going to get cos nt. If we divide the 4n over, we get 1 over n. All right. Again, we're going to use some quite abstract thinking here. I've done it, and I did have made a small mistake here. If I divide this 2 by 4, it's 1 over 2, not 1 over 4. And we're thinking, how can I solve this for n? There's too many variables to solve for n. You probably could make t the subject of this sine inverse of nt, divide n, and then maybe sub it into there. May work, I'm not sure, but we might notice that this and this, that's both the same angle, they're both nt. So we do know that sine squared x plus cos squared x is equal to 1. So sine squared of nt plus cos squared of nt also has to be 1, which means 1 on 2 squared plus 1 on n squared equals 1. And if you go about solving that, you're just going to get n is equal to 2 root 3 on 3. So just solving that, making n squared the subject, taking the square root. All right, that's simple harmonic motion. Thank you.